Thanks, everybody. I'm Jonathan Amsterdam from the Go team at Google, and today I'm going to talk to you about structured logging for Go. So in Go 121, just released, we have a new structured logging package, log/slog, and I'll talk to you about why we're doing this now. I'll give you a tour of the API, talk about how we made it fast and why we made it fast. I'll talk about the whole development process from when we first thought about doing it through the whole community process. And then I'll say what comes next. So why did we add structured logging to the standard library? So let's first look at what we had before. We had the log package, which is very useful for doing formatted printing with log.printf. And that's great for command line programs where typically one person is reading the output. You can change the format a little bit, tweak it a little bit, and you can say where it's going to. And that's about it. So the output is unstructured text, and that's really hard to parse by machine. And you often need that when you're running a server and you're generating tons and tons of log lines, and you need to filter them or categorize them, aggregate them, and so on. There's no levels, so you can't do anything by levels. There's no way to really change the output format, except, as I said, some minor tweaks. So what people do in that situation when they have tons of logs is they move to structured logging. So instead of an unstructured line of text that could be just a natural language sentence, they'll use key value pairs. So here's one way to write key value pairs is key equals value, and people often use JSON for that as well. And we know this is important to Go programmers because there's a ton of these structured logging packages out there, and some of them have quite a lot of users based on the importer count. But that by itself is not a reason we would add something to the standard library. In fact, we're very happy to have tons of packages out there all doing the same thing. But with structured logging, there is the problem that if your application is big enough and you use enough other packages, they'll each have their own logging package that they use. And how do you get them all to talk together? How do you get consistent output, consistent keys, make sure everyone writes the key level and not severity? You have to configure all these different loggers. So our hope was that by putting something in the standard library, there would be a single place, and all these other logging packages, which we're not trying to get rid of, but we're just trying to get to interoperate, they could all use some common framework so that they could all work together. So let's take a look at the API of Slog. Our goals here were to make it easy to use, fast for reasons I'll explain, and to make it interoperate with not only other logging packages, but also log, the logger that comes with the standard library, that came with the standard library before. So our approach was to, there's basically three types involved. There's like a front end, we call the logger, that people will use to actually do their log output. And then there's a back end called the handler that's an interface that you can implement to do whatever you want. You can have handlers actually produce output or wrap other handlers or enqueue things for later processing or just drop the log information on the floor. And it's through the handlers that, by writing different handlers, you can get different log packages to work together. So anyway, let's look at using the logger. So we'll import log/slog, and if you're on an older version of Go, there's a copy of it in the exp repo. And we'll create a new logger with slog.new, and we'll use the text handler for that. That's one of the two built-in handlers that we have. And we'll direct the output to standard out, and then we'll log something at the info level with a message and 3 key value pairs, 3 attributes. And the output is in that key equals value format I showed before. So everything, even the time and level and message, are key value pairs. We'll work together with the log package. If you set the default slog logger to the thing we just created, and then you use the log package, use its default logger, it's going to come out in that key equals value form. I mean, we can't parse out the fields of the message. They just appear as a single key and value. But at least the other stuff is in parsable form. And we can switch handlers very easily to the other built-in handler, the one that does JSON. And now all our output is in JSON, not only slog output, but also output from the original log package. Now, what I showed you with the alternating keys and values is perfectly fine. I think almost everybody will find that fast enough. But if you need extra speed, you can use this log Attrs method. And it takes everything you need, and instead of passing alternating keys and values, you build these Attr things using these constructors like slog.string and slog.int. And they construct this key value pair type. For reasons I'll go into in detail in a few minutes, this is a lot faster than using the other forms, but more cumbersome. So an Attr is just a key and a value, and the key is a string, but the value is not an empty interface or an any, as you might expect. It's some special type called slog.value. And what that exactly is a mystery that I will be explaining shortly. A few other random features of slog. Levels. Slog has levels. Every logging package has its own idea of what a level should be. So in slog, they're just integers that we've named. We've named 4 of them: debug, warn, info, error, the 4 most common ones. There's space in between those things for your own. If you have a level between warn and info, you can assign it an integer, and there's space on it. If you think trace is more debuggy than debug, you can assign an integer to trace. Info is 0 because that's the default value in Go, and that's what most people think of as the default level. And what we ended up with is a fixed offset from the open telemetry logging spec for levels. Their info is not 0, so we sort of shifted it down so it's 0, but otherwise it matches that spec. You can use a level as a flag and then set it into a handler, one of the built-in handlers, using this option thing. And now that handler will only output log lines that are at that level or higher. So if you set that level to info, you won't see any debug logs, which is the default. Now, when you do it this way, the level is baked into that logger and you can't change it. Let's say you want to dynamically change the level. For example, you want to hit an endpoint on your server to switch it into debug mode so you can suddenly start getting debug logs because it's acting funny. You do that with a level var, and all the rest of the code is the same. A level var and a level are interchangeable. But the difference is you can set, as you can see on the bottom of the screen here, you can set the value of a level var dynamically whenever you want, and then all the loggers that you pass that level var to, if you have more than one logger, they'll all change their levels atomically and instantly to that level. Now, sometimes you want to take multiple attributes and treat them as a group. And that's particularly nice with JSON because JSON is hierarchical. You can have a sub-object. So the slog.group function lets you do that. You give it a name, and then you can give multiple key value pairs. And in the JSON output, they appear as a nested object. Another use for groups is when you have 2 subsystems that use the same key with different meanings. Here, in fact, they have different types. So alpha.org uses value as an integer, and beta.com treats value as a string. And some back-end processors, downstream processors of log data, will get very upset if you feed them these 2 lines because they won't know what the type of value is. They won't be able to summarize or aggregate these logs very well. So how can we distinguish the 2 values? We can use groups in another way. We call logger.withGroup, and you pass it a name, the name of the group, and you get a new logger back, all of whose attributes will be qualified by that group name. So when we create 2 loggers and pass them to these 2 different subsystems, we'll get a log line that's where all the attributes of thing 1 are qualified by the name thing 1 in a sub-object, and similarly for thing 2. So that solves the problem of conflicting keys. So Zap calls these things namespaces. We felt it was really the same idea as a group. It's just a group that starts at this moment here when you say with group and ends at the end of the log line. So there's also a logger.with that lets you add key value pairs, lets you add attributes to a logger to get a new logger. So here we're taking the slog default logger at the beginning of an HTTP request, and we're adding the URL path to that logger. We probably would want to add a lot more from the request to that logger, but we'll just do the path today. And we get a new logger that we can then use throughout our request. And as you can see at the bottom, every log message that comes out of that request is going to have the same path in it. So that's a nice convenience. It means that lower levels don't really have to think about, then you don't have to pass the request all the way down if you don't want to. The log output will have what you need. Another thing you probably want to put in here is like a trace ID or some other unique ID for the request, so you can aggregate them together. Another feature of slog is the log value method. Say you have a type and you'd like it to log in a particular way, like as a group with a first and last name attributes. You can write a log value method on that type that returns a slog.value. Here we're returning a group value with first and last name. And then whenever we use that type in a log statement, we're going to get that output. Now, how is this different from writing a Marshall JSON method on that type? Well, it wouldn't be different in this case, but let's say you used a handler that outputted YAML or key equal value pairs or something like that. The log value method, since it just returns slog entities, every handler will process it appropriately, and you'll get the right output for whatever handler you use. So let's look briefly at handlers. Now, most people will never write a handler or need to think much about this aside from creating handlers that they already know they want to use. But we'll take a quick look now and a more detailed look a little bit later at the handler interface. It's got 4 methods, and the main one is handle. As I said at the beginning, a logger creates a record which contains everything in that log event and passes it to the handle method. And so here's a very simple and actually incomplete handler. You'd configure it with some place to write the output to, an I/O writer. And its handle method here prints out some of the top-level fields in a record, the time, level, and message. And then it uses this Attrs function that takes a callback to loop over all the attributes, and it just prints them all out. So just a very simple idea of a handler. Why are Attrs and not, why can't you get the slice of attributes? There's got to be a slice there. Why don't we give it to you? It's a performance optimization. It's to enable a performance optimization that I'll describe for you shortly. Like now, for example. So we wanted to make slog fast. Why? Well, logging can be in the inner loop of your server, and your server processes thousands of requests a second, and each request can generate thousands of log messages, and each of those can take a lot of time. Is that a good reason for making something fast? Not really, because how do you know it's just not fast enough out of the box? I mean, maybe just ordinary Go techniques. I mean, Go is pretty fast just out of the box. So that's sort of a reason. But to really understand why, you have to look at the history of structured logging in Go. The first structured logger that I know about was Logris in 2014. Still very popular, but it uses an inherently slow API. You have to construct a map for every log line. That's going to take some time. So the people at Uber noticed a few years later that their servers were consuming significant time in log messages by profiling. So they built a logger called Zap that was much more efficient. And Zap is quite widely used, second only to Logris. And that started a whole arms race or something of people writing faster and faster loggers. So the first of those that I know about, and still the most popular, is ZeroLog, which is even faster than Zap. And yeah, so this is obviously an important characteristic of loggers, to make them fast. But how fast exactly? We felt that zap fast was fast enough. Because if you look at those numbers, you see that most people are perfectly happy with zap. And the goal of the standard library is not to give you the absolute highest performance tools in the world. It's to give you easy to use and safe tools that are pretty darn performant. And specifically with reference to safety, when we tried to do what Zerolog did, to use their API to get that extra bit of speed, we found we couldn't do it safely, that there's a use after free bug in the Zerolog API. I shouldn't say there's a bug in the API. If you use the API the wrong way, you can have use after free bugs in your code. So it's your fault, not Zerolog's fault. But we didn't want to, that was a joke, not your fault. We didn't want to even have that foot gun in the API. And I'll talk, if you're wondering how you can get a use after free bug in a garbage collected language, I will explain that to you shortly. So we aimed for zap performance, and we did achieve it. And here's how, 4 steps. First, you have to know what you're trying to optimize for. So you have to ask, how will your package be used? And if you can't know that because you haven't written it yet, you have to ask, how are similar packages used? So we looked at a lot of open source code, Zap, and other loggers, but I'll show you 2 results from our analysis of Zap. This is a cumulative histogram of how many attributes are passed to log messages. At the top right, you see a typical Zap log call. Looks a lot like a slog call, actually. And that passes 3 attributes, what they call fields in Zap, a string, an int, and a duration. So we counted those, the number of attributes passed to typical log calls. And you can see here, it's a little hard to read the numbers at the bottom, but basically when you get to about 5 attributes, the rest is sort of a long tail. You've got about 95% of calls use 5 or fewer attributes. I was also curious about those types, the types of attributes. Zap has 32, and I didn't really want to put in 32 different types of attrs into the standard library. So you see, as you might guess, there's a similar cumulative histogram here, where once you get to about 8 types, you've pretty much covered everything, and the rest is sort of noise. So slog has only about 8 of these constructors for attrs. And then there's a constructor called any, which lets you put anything you want in there if you want to put anything in there. So having looked at the data, the next step is to write a benchmark that captures that so you have a target to aim for. So this is a typical benchmark that we use to optimize slog. First of all, since servers run in a highly concurrent environment, there's a request for every there's a go routine for every request, typically. We use this run parallel method in the testing package that will run our benchmarks in parallel. And we use the log attrs call, which is the call that's supposed to be fast. And we used 5 attributes, and we used typical types for those attributes. Now, we also tested with more attributes, 10, 20, 40. But we resisted the temptation to do the thing that every programmer would normally do in that case, which was to factor out common code and, say, make a slice of these attrs and pass different sub-slices to these benchmarks. You don't want to do that with benchmarking. You want to write the call as the user would write it, as this is. And that's because if you change it up, if you used a slice in this case, instead of writing out the 5 attrs, you would get different numbers. The compiler would optimize that differently. So it's always important in benchmarks, I think, to write out the code as it would actually be used. And the last but not least, if you're doing this kind of benchmarking, I highly recommend this program called BenchStat, which I mentioned right at the bottom of the slide there, written by other people on the Go team. If you, like, say, get a benchmark, make a change, get another benchmark, I see people with their cameras. I meant to put a QR code up here, but it wouldn't fit. Sorry. Yeah, so if you do something, benchmark it, make a change, do that benchmark, this will compare those 2 sets of benchmarks. It'll tell you whether it's statistically significant, whether the improvement or regression is significant. And it will even tell you if you need more samples because it couldn't make a determination. So it's a really useful tool. Now let me talk about API design. specifically the design of the handler. So as I said, the logger creates a record and calls the handle method on the handler. So the handle method then is really the only important method, and the other three must be optimizations, which indeed they are. So let's talk about enabled first. That's a pretty straightforward optimization. Many, if not most, log lines never get output because they're for debugging. So you want that to happen really fast. So the handler's enabled method is called right at the beginning of whenever we start logging something. And if it returns false, we just get out of there right away. Pretty straightforward optimization. This next one is due to something that they observed with Zap. We stole this idea from Zap, as we stole many things from Zap. So this with, I talked about the convenience of logger.with, which gives you a new logger that has some attributes in it already, so you don't have to repeat them in every log call. Yes, it's a convenience, but it's also an opportunity for an optimization, because you could take those attributes and format them right at that moment when you call with, instead of having to format them every time you call log.info or log.debug or whatever. So we make that happen by having logger.with, logger.with call handler.with attrs, because it's already been, the logger digests it into these attrs. And then the handler can do whatever it wants with that. It can just save them for later if it wants to. That's the simple thing to do. Or it can actually take those attributes and turn them into a byte slice so that it can just concatenate that into the final result. And that can be a big win if, say, you need to do like a complicated JSON serialization of some struct or something like that. And the fourth method of handler with group is really to enable this, because in order to format these attributes, you need to know what groups are in play at that moment. So that's what with group is for. Now, last but not least, avoiding memory allocation is an important tool to speeding things up. So now we're going from some sort of higher level design and process issues to nitty-gritty stuff. So most of the stuff I'll show you now you should not do, unless you need the performance. And by memory allocation, though, let me be clear. I'm talking about heap allocation. As we heard this morning, there's the heap and the stack. And allocating on the stack is incrementing a register, and deallocating is decrementing a register. You're not going to get faster than that. I don't care how well-tuned your heap allocator is. You're not going to beat that. And even if your heap allocator is just a pointer bump, you still have to account for the fact that there's time spent in garbage collecting the memory you allocated. So heap allocation is always slower. Who decides whether to allocate something on the heap or the stack? In most languages, you, the developer, does. In Go, the compiler does, by doing a technique called escape analysis. It looks at the function, and it says, can this variable escape the function? Does it go into a global or get returned or something like that? If it might escape, it has to put it on the heap. If it knows it can't escape, it can put it on the stack. And the reason is the stack vanishes when that function returns. So anything that might escape cannot stay on the stack. It's got to be on the heap. Escape analysis is very clever, but it's hard to know what it's going to do. So that's where this -m flag I mentioned comes in. If you compile with the -m flag, the compiler will tell you whether something escapes or not, whether it thinks something escapes. It's a static analysis, so it's conservative. If it says something doesn't escape, it doesn't. But if it says something does escape, it may or may not escape. It may just not be able to prove that it doesn't escape. So it's sensitive to how you write your code. And to deal with that sensitivity, it's a good idea to lock in whatever optimization you've done with this function testing.allocs per run. Put that in a test. Say, I expect 3 or fewer allocations here, because that's what your optimization has yielded. And then if someone changes the code in a subtle way to result in more allocations, your test will fail, and you can figure out what's going on. So let's look at a few cases where slog avoids memory allocation, and we'll start with variadic arguments. Here's a really simple function that just adds up a bunch of integers that's given to it as a variadic argument. And inside the function, that variadic argument is a slice. So where is the memory for that slice allocated, on the stack or on the heap? Well, that depends. If you have a direct call to sum, as in that first code block up there, just call the function, the compiler can see that you're calling that exact function with that exact code, and it can see that the Variadic argument does not escape, it just gets looped over, it doesn't get returned or anything. So that first thing will not do any memory allocations because that slice, 1, 2, 3, that slice of 3 integers will end up on the stack. Now in the second block of code, it's hard to read, but the bottom line is on the bottom line. Actually, it's this call to sum through an interface. So when you call something through an interface, the whole point of using an interface is you don't know the exact code that's going to be executed at the call site, and the compiler doesn't know that either, although you might be able to figure it out, the compiler can't. And so it has to be conservative and heap allocate that slice. So that second chunk of code, the call to sum, will cause a heap allocation. What does any of this have to do with slog? Logger is a concrete type, not an interface. People wanted it to be an interface, and we said no for this reason. The log Attrs method, remember that's the fast method, takes a Variadic argument of Attrs. But that call is a direct call because logger is a concrete type, not an interface. And so your Variadic slice of Attrs is allocated on the stack. No memory allocation in the sense we're talking about, heap allocation. And that's true even though the very first thing log Attrs does is an indirect call. It calls handler.enabled. Handler is an interface. That's an indirect call. But it's not a call that includes that Variadic argument, so it doesn't bother escape analysis. So when you have a disabled handler and you call log Attrs, you do very, very little work, not even allocating memory for that slice. Now for this next example, let's turn to the other end of the story, just before you actually are outputting. You, the handler, is actually going to output the data. Now, a typical handler will accumulate everything it wants to output into a byte slice and then do a single call to the write method of an IO writer to output it. So when you build that byte slice, you do it, the normal way to do it is to just declare a nil byte slice and append to it, bit by bit, and that's perfectly fine. You should always do that, unless you have performance data that shows that you shouldn't. So the only thing wrong with that is that, the underlying slice will be reallocated as it needs to grow. It'll start out at some initial size, and then if you add more stuff to it, it'll double in size and get bigger, and that can happen multiple times, resulting in multiple heap allocations. And you can reduce that to one allocation in the common case just by giving the byte slice an initial capacity. Here, so that make statement, the byte slice has 0 length, but it has 1K of capacity. So unless your log message is very long, you'll only do that one allocation, and all those appends will fit into the available memory. You can get that down to 0 allocations in the steady state by using something called a sync pool, which I won't have time to go into detail here, but it's basically a pool of objects that you can take things out of and put things back into. And that way, once you've built up a good-sized pool of these things, you're never asking Go's memory system to do any allocation for you. You're just moving things in and out of the pool. So it's very efficient in terms of memory. And I talk about it. You can read the slog source code, of course. It's in the Go repo. And you can also read about it at this link, which is the handler writing guide that I provided for people who want to write handlers. It's actually not really easy to write a handler because we emphasized the performance aspects, figuring that relatively few people would actually write a handler. So I do recommend, if you want to write a handler, to look at that guide. All right. The next way we avoided allocation, passing records. So logger constructs a record and passes it to the handler. That handler.handle call is an indirect call. So if we passed a pointer to a record, it would be heap allocated because escape analysis wouldn't be able to prove that it doesn't escape. And indeed, it might escape. A handler might take that record and give it to something else, put it on a channel or something like that. So how do we avoid allocations there? We don't pass a pointer to a record. We pass the record. We pass it by value. We copy it. And by copying it, there's no question of whether it's allocated on heap or the stack. It's simply memory that's copied from one function to another. Now, inside that record, as I said, there must be a slice of Attrs, because you could provide any number of attributes or key value pairs that you wanted in your log call. We know that slice has to be there. And indeed, normally that's fine. That's all you need. You should ignore that red line. Just use a slice. Perfectly fine. But if you care about memory allocation, you want to be more clever. What about a sync pool? We can't use a sync pool here. I mean, technically we could, but it would be a bad idea, because records are things that users can get their hands on. Anyone can write a handler and get a record. That means either they have to return the record to the pool themselves, or we could do it for them. Say at the end of handle, we say, we'll free that record for you. We'll return it to the pool. But if we did that and they actually held on to the record and used it again, what would they have? A use after free bug. The thing that you thought might not have been possible in a garbage collected language is if you expose a pool allocated data structure to the users. And that's exactly what Zerolog does, and why we couldn't take advantage of its clever API to get any faster than we've gotten. So what did we do? Well, we put a little array in the record. The array is allocated with the record, which is allocated on the stack because we never create a pointer to it. It's passed by value. So there's no extra allocation there. But that's only true if you have n or fewer attributes. Once you go over n, we'll use that slice. So what should n be? If it's too small, then we'll overflow to the slice a lot, and we won't see the benefits of this optimization. If it's too large, the record gets big, and remember, we're copying records. So there's still some time involved in copying that memory. Well, luckily, we figured this out in step 1. We figured out that most calls are 5 or fewer, so n equals 5. And we know we're going to get about 95% of the calls with our optimization. Last but not least, I promised to tell you how values work. So an attr, remember, is a string and a slog.value. And when you construct an attr with slog.string, for example, it calls that string value function to construct a value. So a value is like an any, an empty interface, but it's a little bit bigger, and that lets us get rid of allocations in some common cases. And I'll specifically talk about strings here. So to understand this, you have to understand how Go represents various things in memory. So this is an interface, any interface. It's got 2 machine words, a pointer to the data, and some information about the type. A string is also 2 machine words, a pointer to the underlying bytes, and the length. And when you put them together, sorry, yeah, you can see that thing at the top right. I just noticed that. Sorry. I'm not sure how to get rid of that right now. Just forget about it. So when you put these 2 together, and you put a string inside an any, you get a pointer to a pointer. You get 2 memory allocations. Now, the one on the right, the string, you can't do anything about. But the one on the left, we're going to get rid of. That's, in most cases, that's going to be a heap allocation, just by putting a string into an any. Let's look inside a value. A value is an any, but it's also got one other machine word in it we call num, an unsigned int. And like reflect.value, a value has different kinds, these small integers, this enum, that tells you what kind of value is in there. So let's start by talking about some simple types that we can represent in a value, like an int64. we simply use the num field for the integer, and we use the any field for the kind. Now, I said that in an any, or any interface, the value is a pointer. And that's true. So why isn't there a memory allocation when we put this integer into that any? And the answer is there's an optimization in Go that for small integers, there's a built-in table in the runtime of the first 1,000 or so integers, and you get a pointer into that table. So it is a pointer, but it's a pointer to statically allocated memory, not heap allocated memory. We do the same thing with floats, except we use this function that converts a floating point number to an unsigned int. So nothing interesting there. But now let's look at how we do strings. So to construct a string, we put the length in the num field, and we put the raw data, which we get with, that is the byte pointer to the bytes, which we can get with unsafe.string data, we put that into the any field. But we wrap it in a type of our own, an unexported type, that tells us that this is what's there. So the function that pulls this thing out can make sure that it was, that data was actually constructed with this string value function. And the picture at the bottom is the story. We now just have the pointer to the bytes. We do not have that extra pointer. So we've saved an allocation. And that's why we have this value type. It's just to save allocation. All right, let's pull back away from all the technical details and talk about the process that we went through to get from when we decided to do slog up until it was released. So way back in April 2022, over a year ago, we decided we'd gather enough data. We'd seen there's a lot of open source packages. We'd heard a lot of people asking to have some sort of way of unifying these things. And we decided to explore adding structured logging to the standard library. So we looked at the existing structured logging packages and their APIs. We looked at the usages of them. And we came up with a preliminary API that we shared among the Go team and other structured logging experts inside and outside of Google. And that led to a revised design. We did another iteration. And then we felt we wanted to go public, share this with the community. So we started a GitHub discussion, which we use now for large changes to Go because it's got a better threading model than the GitHub issues. That discussion got about 300 comments. It led to a number of changes and additions. We added groups there because someone mentioned, several people mentioned how important they were. And in about 2 months, we felt we were ready for an actual proposal. So we put a proposal up on the issue tracker. That got about 800 comments in all. We made more changes, additions, removals. And then in March, even though there were still some unresolved issues, that proposal was accepted. And then, not shown here, because there's no room, there were 10 more proposals for little bits and pieces that we hadn't quite figured out. But we knew we had narrowed things down to just those few isolated parts. And this single issue was getting a little hard to read. If you've ever read a long GitHub issue, you know how painful that can be. So those 10 proposals were all dealt with, either rejected or accepted within a couple of months. And we finished our implementation. And on August 8th, slog was released in 1.21. So let me share with you a few highlights of that whole process, the community process. So one question we got was, why is this being proposed now? Why not 5 or 8 years ago? And that's a good question, and I think I've tried to explain that we had to wait and see, that it was actually an important problem for the community, and that there was a challenge in interoperating all these different log packages. And generally, as you know, Go is conservative, so we waited. But something about the syntax of this question made me think to myself, well, if we had designed the time machine and we'd succeeded, slog would already be in the standard library, so I guess we failed. So how about we just do it now? Let's just do it now. All right. This is a piece of API we had in slog until we took it out. And the reason it was there was, first of all, so what it does is you can add a logger to a context and then take it out when you need it. And I use this all the time. I think it's perfectly fine to do that. And it's useful because you can plumb a logger through multiple levels of code that don't care about logging until you get to something that does care about logging, since you're probably passing a context along anyway. And by my rough count, there's already 100 packages that do something like this just for Zap alone. But this got a lot of negative comments. Logger smuggling, anti-patterns, hard enough to find anti-patterns when the Go standard library is supporting these, blessing them. Other people said it's fine, and we do it all the time. But we ultimately decided to remove this because it's a small piece of the API that's separable from everything else. You can sort of add it yourself. You won't have the same context key as someone else will, so you can't really interoperate that well. Hopefully, maybe somebody will say, let's just use this one context key in my package here, and then we can all work together. But we just felt it was too controversial to put in our standard library, and we can always add it later. Alternating keys and values was the most controversial part of the whole thing, believe it or not. People who hated this really hated it. Breakage, disapproval, get rid of all convenience shortcuts, all of them. And my favorite, I hate passing attributes as keys and values from the bottom of my heart. People felt it was just not type safe and you could make mistakes. And they're right, you can make mistakes. You can leave out, if you leave out a value and you don't actually have literal strings, it's a little hard to see. But here we decided to keep it. For one thing, you can actually use slog info with those attrs, like slog.string and stuff. But that's not a good answer to the people who were complaining. They were complaining about other people using it and having to read their code, which I totally get. We also knew from looking at other logging packages that there are many successful logging packages that use alternating keys and values. We'd never heard of any horrible things happening from doing that. And we added a vet check, by the way. There's a vet check that will, it can't always succeed, but it does try to find mismatched keys and values. I think the fundamental reason we kept it, though, is this. If I had to pick one word to describe Go, it would be light. Go should be easy to write, easy to look at, and especially for logging. Logging is not your main business logic. It's something you're putting there. You're taking extra effort to put there in the hope that it may be useful someday, and you don't want to spend a large amount of time writing and looking at these cumbersome log lines. So for all those reasons, we decided to stick with the key value syntax as the main syntax. And this goes to show that these proposals on the issue tracker are not popularity contests. And I think that's really a good thing. We all know what can happen if you end up with a popularity contest that doesn't always work out the way you want. So summary of the community involvement, my personal feeling. I thought it was incredibly valuable. It changed slog dramatically for the better. I thought all the comments were thoughtful and professional. I personally found it inspiring to collaborate with the whole world on something. That's really exciting. And it was a lot of fun. So thanks to everyone. If any of you are here, thank you for participating in that process. It was very valuable. What's next? Well, now that slog is in the standard library, of course, everyone will throw away all their existing logging code and only use slog. No, seriously, new code will probably start using it, but do not throw away your existing log code. It's perfectly fine. All the loggers I mentioned are perfectly fine. It's just churn to remove that stuff and put in slog. But we do hope that with the handlers that are being written now for many of the loggers, you will find a way to pick a single handler and install it in your main application and have all the logging loggers from different packages work together. And that was our original goal. So here I did put QR codes up. The pkg.go.dev link will tell you, give you all the documentation for slog, but there's also a wiki page that will show you other resources like handlers people have written. a whole bunch of handlers, colorizing text, all that stuff that we weren't going to put in the standard library, but are there. And if you come up with something, you can add it there too. I hope you enjoy using slog as much as we enjoy designing and building it. Thank you very much.